Yes. So this is the method number one, based on symmetric key. You hash, and then symmetric encryption. Number two, you hash, and then private key. Number three, you avoid encryption altogether. In that case, you don't have to go through encryption, which is nice. Okay? Because encryption is complex. So we add the secret value with the message, and then we hash everything. So this way we don't have to do encryption. طيب, بسم الله الرحمن الرحيم. So we started to talk about hashing functions. We said that hashing is required for developing or estimating the message digest or the digital signature for any arbitrary sized message. So these are the very important requirements for any hashing mechanism. So the hashing mechanism can be applied to a block of data size, any size, okay? So regardless of the data size, we need to provide fixed size hash. So the hashing mechanism should provide a fixed length output, okay? So regardless of the message itself, we need to provide fixed size hash. The hash of any message is relatively easy to compute, okay? So the complexity should be low, because otherwise we can logically use encryption to provide message digest, okay? We can do that. We can sort of manipulate the encryption, because we know that encryption works on a fixed size block, right? But we can divide the message into fixed size blocks, right? And then do encryption in a blockchaining fashion, as we will see. So يعني احنا ممكن نتحايل يعني, we can do this. However, we want to avoid using encryption. Why? Why not use encryption?
No need to get back to the original message.
Reversibility is not needed.
Yeah.
صح, بس if I have reversibility, it's okay. It's an added يعني thing. يعني it's not a big deal يعني. In fact, but we want to make reversibility hard. Okay, we want to make reversibility very hard. And also, encryption is highly complex. This is the main reason. We want to avoid using encryption, because encryption is highly complex. Complexity is really high. Okay? So, unlike encryption, طبعا especially DES مثلا, as we have studied before, DES is good for hardware يعني implementations, right? Because it works on the bit level and so on, right? Hashing functions, as we يعني may observe on the internet and whatnot, it's widely يعني available in many formats, in software and hardware. Why? Because they are less complex, much less complex. Okay? So number 4 is very important. For any given code or message digest or hash, okay, it is computationally infeasible to find message X such that h of X equal to H. يعني, if I give you H and tell you, okay, calculate X, which is the reversibility bar, okay? So this talks about the fact that not only do we not need reversibility, we need to make it hard. We need to make it hard. Even though, if even يعني طبعا, is it possible to get this X? Theoretically, yes. احنا عشان كده بنقول ايه؟ احنا we did not say it's impossible. It's always possible. Okay? But it's computationally infeasible. Okay? Because it's always possible. Okay? But even if you get X such that h of X equal to H, okay, does that mean that this X is the one that I've used? No. We'll see why now. There's no guarantee. Okay? So number 5 explains that. So for any given block X, if I give you now X, okay, can you calculate H? Yeah, this is what we're trying to do. We can calculate H very easily, right? So from X, okay, we can calculate H of X very easily, okay? We know how to do this. However, it is computationally infeasible to find Y. Y, it's another message, okay, such that H of Y equals to H of X. This is not reversibility here. This talks about the fact that if I give you a message, okay, this message is X, okay? This message has specific H, okay? So now, can you do any permutations on this X, okay, such that in H will remain the same? Okay. Again, theoretically, is it possible? Yes. But we want to make this computationally infeasible. We cannot say it's impossible. Okay? And I will tell you why now. So, the last one, it is a computationally infeasible but to find any pair of messages. Now, I didn't give you X. If I give you X, you say, okay, so I will permutate X to get Y. Okay? Here, in number 6, you have all the degrees of freedom back. Any two messages, such that H of X equals to H of Y. Again, it's computationally infeasible. So I didn't give you any message initially in that case. This is the difference between number 5 and number 6. Number 5, they call it weak collision. Weak collision because I gave you already X. So you need to manipulate X to get to Y. Okay? Number 6, they call it a strong collision. Strong collision here means that any two messages, they can collide. So why there is always collision, theoretically? Okay? Why there is always collision? The size of H, okay, if we assume that the size of H is N, and the size of X is M, what is the relationship between M and N? M is, in fact, much more than N, typically, right? صح? Usually, I have a very long message, and I need to calculate a small message digest, right? Type, what is the combinations of all the possible hashes? It's actually 2 to the power n, right? What is the combinations of all messages on Earth with size m? Okay, it's 2 to the power n, right? So no matter what you do, there is no one-to-one relationship. Why? Because the number of combinations on the messages are much more than the number of combinations on the hash. So this relationship always applies, right? Okay? So there is no one-to-one relationship. Okay? So there is always collision, theoretically, huh? But we want to make it as hard as possible. This is the requirement. إذن, the summary of this is that we want to make the reversibility hard or computationally infeasible, okay? And we want to make all forms of collision, weak collision or strong collision, we want to always make it also computationally infeasible or hard. مفهوم كده؟ So this is the requirement for any hashing mechanism. طيب, an example of a hashing mechanism which is very lousy. Okay? We talked about the fact that in networks, one of the very easy techniques that we usually use to detect errors, okay, is what we call CRC, okay, cyclic redundancy codes. So this is made for detecting errors. Okay, so detecting errors might give us a clue. So because detecting errors معناها ايه? If the message is manipulated or the message is have changed, okay, then the CRC will detect that error. Okay, so this is what we want to do for hashing. Okay. Okay, so can we actually use CRC for hashing? Because if we can, this would be very easy. Okay, because we know how to do this in networks. We've been doing this in networks, right? But the bad news is that this is not possible. Why? Because these CRC codes do not preserve the properties that we just talked about. Okay? Reversibility is okay. If I give you the hash, okay, it's hard to get the message. Or in other words, you can get plenty of messages. You won't be able to tell which message I used. Okay, because to reach from that CRC code to get the messages, there are tons of messages that can produce that code. Okay, so by the way, the CRC is very simple. What we do is that we get the message. It's a very, very long message. What we do is that we order this message in words. Each word is of size n. Okay? So in general, if the message has any length, I can apply this. But if the message size is not divisible by n, what do I have to do? And if I have a big message, but the message is not divisible by n, by the size of the block, what do I need to do? In networks, what do we do? Dummy bits, padding. We call it padding. Okay, so I can do padding. So that's not a problem. We know how to do this, right? So once I order or arrange the message in blocks of n, I can put them like a multiple rows stacked كده, and then I calculate the number of ones. Or in other words, I do XORs. If it's even, then this will be 0. If it's odd, then this will be 1. That's it. I do XOR on all these rows. So that's very easy, okay? So if I give you 0, 1, 0, 1, can you actually generate the original message? You can generate tons of messages that can produce the same CRC easily, right? But you won't know which message I actually used. So reversibility is not, it's not a problem. The more problem is the collision. Because imagine if I give you message X, okay? If I give you a message X, you will be able to calculate the CRC very easily, right? Okay? Type. If you change some bits, so I give you like, for example, 1, 1, 0, 0. Okay? So if you bring this 0 here and this one here, will it produce the same CRC? Yes. Of course, because the XOR will not be will not change, right? Did you actually manipulate the message? Yes. I have produced Y very easily, actually. Right? So the weak collision is not achieved here. And I can manipulate, I can give you tons of messages with the same CRC values. Okay? So the weak collision is not achieved. So CRC is not a good way for calculating the hash. That's bad news, so we need to work on that. So we need to come up with other techniques to do this. So NIST, in 95, they came up with a standard called SHA. And SHA is very common. You might have come across this on the internet. You see حتى many files on the internet, they use SHA or MD5 or MD4. Okay? They use it for hash. Why? Because they don't want people to manipulate the file okay, and add some viruses to it. So anyone can actually manipulate the file and add some virus, okay, and you won't be able to tell that this file has been manipulated, and this way they can spread viruses everywhere. So in order to make sure that these files are not manipulated, they add to it some hash, okay? That's why if you see the file with hashing, usually this is more trusted, except that you won't be able to tell whether this hash was created by the original owner of this file or maybe by the hacker himself, regardless. So SHA was a standard technique that was developed by NIST, which is based on MD4. So MD4 existed before, and they have built SHA on top of that. However, in 2005, NIST announced their intention, and we'll see now why. Because of the fact that we know that collision is always there, right? We said that. Collision is always there. And this is because of the fact that hashing does not guarantee a one-to-one relationship. So theoretically, the collision can be achieved. Okay? So there is a theorem. It's called حد عارفها؟ birthday paradox. Okay? It says that for any hash, okay, of size n, you can achieve two messages with the same hash with a complexity of, on average, O to the power 2, O of 2 to the power n over 2. n over 2 مش n minus 1 ها كنا قلنا في البروت فورس عامة. Okay, in brute force what we do is that by half is a 2 to the power n minus 1. Here you can achieve the collision, okay, with a complexity of 2 to the power n over 2. Okay, طيب. So it's a function of n. So the problem is that SHA was had a length of 160, as we will see, 160 bits. So regardless of the message size, we produce a hash of a length 160. Okay, so in that case, the complexity of the birthday paradox will be a 2 to the power 80. 2 to the power 80 is very much feasible to be done even by cell phone. You can achieve this collision very easily. Okay, so that's why they try to complicate this even more, and they have produced SHA-2. Again, this is not to say that SHA itself is not a strong hashing mechanism. It's just that by physics, يعني, by the limitations, you can always achieve that collision using a complexity of 2 to the power n divided by 2. In that case, it's very much achievable. HMAC, so in that case, SHA itself, as we can see here, it performs some, it divides the message into blocks. Okay? So this is SHA-2. So this block diagram describes SHA-2. Okay? And SHA-2, in that case, it produces a hash of size. شوف, SHA-1 was a 160. This one is a 512. Okay? So the birthday paradox, the complexity is 2 to the power 256. Okay? Which is hard. Supposedly it's hard. So what we do for SHA-2 is that first we divide the big message into blocks of size 1024. So what if the message is not divisible by 1024? We add the padding. So this is the padding. Okay? And the padding is simple. As you said, it's dummy bits. Okay? So we add 1 and all zeros. But we need to keep here 128 bits to to have or to represent the length of the unpadded message. So that when you read the message, okay, you read the last 128 bits, you know exactly the length of the unpadded message, and all the dummy bits you throw it away. ماشي كده؟ So that's easy. So the message can be divided into 1024 bits aligned. Okay? Unlike the CRC, we don't stack them on top of each other. This is naive. يعني. We don't do this. In order to make the hash really collision proof, or at least يعني, collision resistant, we need to make that a blockchaining. We need to make that blockchaining. Okay? So what we do is that we start from an initial hash, which we call it a initial vector. This is a initial vector, and this initial vector is an arbitrary hash or arbitrary number. Usually it's a prime number or something like this, but it's pre-configured. Okay? It's given. And then we take the first block, we apply a function similar to the round function of the fizzle structure, remember? Or AS. But here, this round function does not perform a transposition and permutation and stuff like that, because this is highly complex. This one, what it does is that it uses a combinations of XORs. A combinations, so it does like circular shift and then XOR, circular shift and then XOR, because this is a less complex. But the idea is the same. And then the output, we do some modular addition. We do some modular addition. So when you see plus and then square around it, this is not XOR. This is a modular addition. Okay? And this modular addition is mod 2 to the power 64. Okay? So, and then we take this hash and then we apply the same thing on the next block. So we do that block chaining. We do like some pipelining of block chaining like this until we get to the last block. We produce that N, and this HN will be the one that we use. Okay, so this is the ultimate hash that we use. Okay? طيب. So this is how SHA-2 works. So this way it's much less complex compared to the encryption algorithm, okay? Because it does not perform this transposition and permutations and stuff like that. And it produces a fixed size hash. And as you can see, if we can again try to do similar to what we have done for fizzle structure, if we can try to convert this into an equation. Okay? So any hi equals to what? Equals to the hi equals to a function here, the round function, which is a function of two things. The block I and hi minus 1. Okay? صح كده؟ And then we do modulo addition between this and hi minus 1. Right? So again, it's a nice recursive equation that information theorists can take that equation and they can say, okay, so let's see if we can analyze this from an information theoretic point of view and reach to the fact that we can really perform collision here using close to the first day paradox. Because if we can, like CRC مثلا, if we can perform the collision, if we can achieve the collision, okay, with O of 1, we can do that for CRC, right? The complexity is O of 1, okay? I can just change the location of 0 and 1 in one column, and I can do the collision, right? So if I can do this, then this means that the hashing mechanism is not strong, okay? So they can take that equation and they can perform the analysis.
What's the operation in the function? Function.
ما أنا قلت the operation in the F function, unlike بقى the encryption, the standard itself على فكرة does not dictate this, but generally it is a combination of XORs, a combination of the same message. We take it, we do a circular shift XOR, circular shift XOR, and so on.
So it will happen 523 times? The XOR will happen for each block like 5.
No, here, remember here, the size of the message is 1024. The size of the hash is 512, right? What is the size of the output here? It's 512. ماشي? So that's how the input and the output looks like with regards to this round function. ماشي? So this output gets modulo added with the hash from the previous step, and then you get a size of 512. And then you do this again and again and again and again. ماشي?
The initial value, is it random or?
The initial value is arbitrarily chosen. ماشي? Based on random number generator usually. So usually they use random number or pseudo random number generators to generate these IV values. We'll talk about this as part of the protocols. So usually when we come to explaining security services, very commonly they use some pseudo random number generator to generate many of these random numbers in the system. They generate بقى مثلا IVs, as we will learn later. There is P and Q for RSA. So they generate these random numbers very commonly. Okay? But for SHA, IV is just an initial vector. They call it initial vector. ماشي? It's arbitrarily chosen.
But how the 1024 will be 512?
You can do that easily. ما احنا قلنا بقى يعني you can take the 1024 and then perform some circular shift on each 512 مثلا, because 1024 divided by 2 is 512.
The XOR will give me the same number.
Yes, but what you could do is that this 1024 you can divide it into low 512 and high 512, right? And then take the low 512 and then perform XOR مثلا with the IV, right? And then the result would be XORed with the other high 512 and so on. You can do that easily. So inside the function you can do whatever you want, but usually they do more than this. They do more than this. They don't do بس 2 XORs. لا. They try to perform some circular shifts, because 2 XORs again will go back to the CRC issue. But they try to do some circular shifts and perform multiple steps of XORs so that again you make the collision harder. That's the issue. For us, we don't have to study the details of this round function, okay? But what we need to know is that this function, again, is based on XORs, which we know how to do. Software and hardware is very easy, right? It's very easy. And it's not like encryption, where we use permutation, transposition, and manipulation and stuff like, which is highly complex.
That's what I want to ask.
Yes, it's highly complex. It's very highly complex. So hashing mechanisms are much less complex compared to encryption. But the idea of producing this equation makes it easy for anyone to visualize and understand how it works, and also for information theoreticians to try to analyze the effectiveness of this hashing mechanism. ماشي كده؟ Based on this third. So, طيب, SHA itself produces what we call message digest or hash. Message digest is good for what? is good for integrity. Right? Integrity معناها if the message is manipulated, you can detect that the message is manipulated, right? And then you make it hard for any attacker to manipulate the message and perform the same hash, which is what we call collision, right? Okay, so SHA can perform this, but it does not fulfill the requirement of message authentication, because message authentication requires some kind of a fingerprint of the source who sent the message. Hashing does not do that. So definitely the key can perform this, right? Or, as we have discussed last lecture, what we call a secret value. So if the sender and the receiver, they agree on a key, the key can be used in combination with the hash, right? To make sure that the message is coming from an authorized source. And at the same time, the hash makes sure that the message is not manipulated. Okay? So the hash achieves one objective but not the other. So we still need another technique, okay, to work hand in hand with the hashing to make sure that the message is coming from the right source, and also ensure the non-repudiation. Non-repudiation talks about the fact that the source cannot deny later on and say, no, I did not send this message. No, the message was sent with your fingerprint into it. Okay? So the HMAC هنا, from the name, it's hash-based message authentication code. ماشي كده؟ It's hash-based message authentication codes. Message authentication codes is what we have discussed before. اللي هي ايه بقى؟ It's required for both, or it achieves both. ماشي؟ Authenticating the user in every single message and making sure that the message has not been manipulated. ماشي؟ So cryptographic hash functions generally execute faster in software, which is good, but it does not achieve the non-repudiation part or the authentication of the user. Okay? But it's good, and it's better than the conventional encryption algorithm, which also, by the way, it can be used for hashing with some manipulation. But the problem is encryption algorithms are complex. Exactly. ماشي? So a hash function such as SHA was not designed for use as a MAC. Okay? It's designed only for the signature part or the message digest part, but not as a MAC, because MAC requires authentication. ماشي? Because it does not rely on a secret key or a secret value. It does not have that part. Okay? So there have been a number of proposals for incorporation of a secret key into the existing hash algorithm. For that purpose, they said, okay, so we can incorporate a key, okay, with the hash. Okay? And as we discussed before, this can be done in 3 different ways. Whether using symmetric key, encryption, okay? So we produce the hash and then we encrypt the hash, right? Or using public key encryption, okay? So in that case, we produce the hash and then we encrypt it with private key, bravo عليك. Private key, not public key, okay? Or the third way, which is, instead of encryption, we use secret value. Okay? HMAC is based on the secret values, based on this third step. Okay? A whole method. Okay? And HMAC has proven to actually achieve very good security protection or very strong message authentication codes. Okay? Without having to use encryption, which is highly attractive. That doesn't mean that encryption will not be used at all, because we still need encryption for what? what is the security objective that we need the encryption for?
Transmission?
What is the security objective that we need the encryption for? Here, we are trying to address integrity and non-repudiation, right? But we did not address what? Confidentiality, yes. Okay? For confidentiality, there is no work around it. You have to use encryption. Okay? But you still need to achieve all of them. Okay? Which means that you need to do encryption for confidentiality because it requires also reversibility. And then for integrity and non-repudiation and other things, you can use the MAC. Okay? So, as you might think, what we do is that we can say, okay, so we can have, this is the message, and what we just said is that we can add, instead of doing by encryption to the hash, what we can do is we can add the secret value or the key to this message, and then hash everything, right? This is what we said, right? HMAC tries to be a little bit more protective from a security perspective. So we do that in 2 steps. Okay? So the only thing here is that we do that. HMAC performs this same concept, but on 2 steps. So what we do is that we take the secret value or the key. This is the secret value or the key. Okay? And we perform masking. This is masking. So we have an iPad and OPAD, which means that we take that secret value and then we mask the lowest part and the highest part. It's like you divide it into 2 parts. ماشي كده؟ واضح كده؟ Then you take that lowest part and you put it as a secret value 1. And you put it with the message. So instead of having the whole secret value, we have only the lower part. ماشي? And we put it with the message. And then we perform SHA based on initial vector. So here the initial vector will have a size of 512 مثلا for SHA2, right? So the output here will be 512. And we get the hash of 512. This is for SHA2, right? Okay? So here, we will deal with this hash as a message on its own. But here the message is of size 512. The message size here is fixed, 512. Right? And then we add a S0, which is the upper part. Okay? So we do that on 2 steps. And then we add the secret, which is also based on the key or the secret value. It's just that this is the upper part of that secret value. We add it to the message, which in that case is of fixed size 512. And then we do the hashing again. So we perform hashing twice. Why? Again, just to make the collision harder. ماشي? Can we do that on 1 step? Yes, we can, of course. But the standard itself recommends having this done this way, on 2 steps. Okay? And this is, again, based on experiments, they found that this will make the collision harder. ماشي? And also will preserve more the security protection. We'll have more security protection in that case. Okay? So, here, the user has his own fingerprints in that key. So this is the authentication part. And the hashing will ensure integrity. Together, we have the MAC. So this is called the MAC. It's not hash anymore. This is called HMAC. ماشي كده؟ Any questions? واضح كده؟ Yes. These are masks. Yes, masks. عشان بس تاخد مثلا this is the lower part of the key or the secret value, and OPAD will allow you to use the upper part. Yes. This is just masking. Again, these are these masks are also pre-configured, similar to IV. Okay? So it's like you can perform all of these using functions, and these are parameters in the function. IV, OPAD, IPAD, things like that. ماشي? And of course the key. ماشي? Any question? So it's like it's similar to secret value, but we do that on 2 steps. I did not include it. Here, this block chaining can be done using encryption. So instead of doing encryption for the whole message, what we do is that we take this, we apply encryption, okay, and then we add it to the next one. So we do the encryption based on block chaining. We can do that, right? But the problem is that encryption is very complex. This is HMAC, and HMAC has proven to have good security protection and good collision performance, and at the same time it does not use a encryption, which is good. ماشي? There is of course another way of producing MAC, which is called CMAC. CMAC is based on cipher-based message authentication codes. So HMAC is hash-based, but CMAC is based on cipher. In that case, we use encryption. You see? Why do we use encryption in that case? To make the security protection more. However, it's very complex. Very complex. So anyway, here we talk about the public key encryption. Public key is a brand new topic, and here we talk about 2 keys, okay? And unlike all the symmetric encryption, here we are based on calculating the modulo arithmetic properties of the numbers. So I'm not sure to what extent you have studied this, and I will talk about high level, the protocol from a high level point of view. But if you need some mathematical background about this, which we do normally in the master level, I will not have to go through this here, of course, because you should have studied this in applied cryptography. It's not in the scope of the course, but if needed, I can explain this to you offline. But the idea is simple. You need to know that in public key cryptography, in general, we have 2 keys, one private and one public. The public is to be shared with others, okay, whereas the private is private to you, and you should not share it with others, right? So there are a number of these public cryptography, and you need to understand how you can use each one of these. Because, for example, RSA can be used for encryption, can be used for other things, okay? But, for example, Diffie-Hellman cannot be used for encryption. So you need to know these things. This is very important. Diffie-Hellman is the first one, which was invented in the 70s, and it's not suitable for encryption. It does not have reversibility aslan. Okay, so it does have private key and public key. It does have 2 keys, but it can be used only for what? حد فاكر?
Key exchange.
Bravo عليك. Yes, for key exchange. We should have some bonuses. Should do this. So public key encryption is based on mathematical functions. It's not based on simple operations بقى or transposition or permutations زي ما احنا عملنا. لا. Here the idea is different, totally different. ماشي? So the main advantage compared to symmetric keys is the simplicity of the key distribution. Again, simplicity. It's not. Some people they think that key distribution for public cryptography has 0 overhead. No, it has overhead. It has some overhead. So we'll talk about this. It's not 0, but it's definitely less than the symmetric key. Why? Because while you're exchanging the symmetric key, if the symmetric key itself is leaked, خلاص, the whole thing is done, right? But here, I can give you the public key, it's public. خد اللي انت عايزه. Okay, I still have the private key. So that makes the key distribution simpler, but it's not 0. we'll talk about why. ماشي. So we'll stop here عشان بس نعمل